by show of hands, how many of you have heard the word screening? You don't really have to raise your hands for this, but I guess most of us have heard about this word. But I'm not talking about screening in pageants nor in jobs. I'm talking about screening as a unit operation. Now in this presentation, these are the points to discuss, starting by the theory and significance of screening, or particularly the sieve analysis. Next would be objectives, materials and equipment of the laboratory experiment, the procedure by showing a flow chart. Next would be data, equations and calculations, and the last part would be conclusions. Good day to all. Today I am going to assume that most of us here are taking particle technology in this cluster. Am I correct? Now, from what was discussed a few weeks ago, may I have a volunteer to give me a brief introduction on what actually is screening? Now again, as what we have mentioned, sieve analysis is the method of particle size analysis, using which we determine the amount of particles of different sizes present in the soil sample. Sieve analysis is done for coarse-grained soils, and in this method, soil is sieved through a set of sieves. Sieves are wire screens having square openings. Size of these openings gives the sieves their name, which is called the sieve number. A sieve with a mesh opening of 4.75 mm is designated as 4.75 mm sieve. Similarly, a 600 micron sieve refers to a sieve which has a mesh opening of 0.600 mm. Sieve analysis itself is done in two ways. We have dry sieve analysis and wet sieve analysis. Now this time we take roughly 500 grams of soil sample. Now it should not contain any lumps into it, and if it does, then lumps should be pulverized. We take its weight and say this weight is capital W. Now this sample is sieved through 4.75 mm sieve. The portion of soil which contains particle size bigger than 4.75 mm is retained on the sieve. This portion is then called the gravel fraction. The portion of soil which contains particle less than 4.75 mm pass through the sieve, and this portion will then be called sand fraction. This way, coarse-grained soils are divided into two categories. We have gravels, having the grain size greater than 4.75 mm, and we have sand, having grain size smaller than 4.75 mm. So for the sieve analysis of our sample, we will need two sets of sieves, one for the gravel fractions and another for sand fractions. Now for gravel fractions, we require sieves of sizes 80 mm, 40 mm, 20 mm, 10 mm, and 4.75 mm. This set is called set of coarse sieves, as it sieves coarser parts of the coarse soils. Second set of sieves is for sand fractions, consists of sieves of sizes 2 mm, 1 mm, 600 micron, 425 micron, 212 micron, 150 micron, and 75 micron. If we didn't mention, then 1 mm, that is millimeter, is equal to 1000 micrometer, which we denote as a letter micron. So 1 mm is equal to 1000 micron. So here is 600 micron. So this actually means 0.6 mm. Now this set of sieves is called set of fine sieves, as it sieves finer parts of the coarse soils. Now the sieves are stacked on one over the other with increasing size of their mesh openings from bottom to top, which means the sieve of the largest opening is kept at the top. A pan, which has no opening, is placed below the bottom of sieve. The soil sample is then placed in the top sieve, and a lid to cover this arrangement is placed over the topmost sieve. The whole arrangement is then placed on a mechanical shaker and is shaken for 10 minutes. Then arrangement is taken out, and the amount of soil retained on each sieve and pan is weighed with the accuracy of 0.1 gram. Now let's say the weights retained on the sieves are W1, W2, W3, W4, W5, and W pan. Now then we calculate the percentage of the amount of soil retained on each sieve as weight of retained soil on the sieve divided by the total weight of soil sample multiplied by 100. Now this way we know what percentage of the total weight is retained on the particular sieve. Percentage weight retained on the first sieves is W1 divided by W multiplied by 100. Now let's say these percentage as P1, P2, P3, P4, and P5, and P. Now for calculation purposes and to determine some important characteristics, we also calculate two values. First one is the cumulative percentage retained. Now let's write all these calculations in a table. Now cumulative percentage retained on any sieve is percentage weight retained on that sieve plus all the percentage weight retained on all the sieves above it. Cumulative percentage retained is the total percentage amount of soil which could not pass the particular sieve. In other words, this percent amount of soil has grain size greater than the sieve number. Now let's calculate all the cumulative percentage retained for each sieve. Now the second value we calculate is for the percentage finer, using which we plot a graph called particle size distribution curve. Percentage finer, as name suggests, is the percentage amount of soil which is finer than the particular sieve. Consider any sieve from the stack. Now the amount of soil above this sieve is coarser, and its total weight in percentage of the total soil sample weight is cumulative percent retained on this sieve. And the amount of soil below the sieve is finer portion of the sample, which has particle size smaller than openings of this sieve. Total weight of this portion is percentage of total soil sample is percentage finer of this sieve. Now this can be easily calculated by simply removing cumulative percentage from the 100% of soil sample. Now we can complete our table. The whole procedure I discussed is dry sieve analysis. The finest sieve used in the analysis is 75 micron. Now if the portion passing through the 75 micron sieve which we collected in the pan is substantial, say 5 to 10%, then wet sieve analysis is carried out. The purpose of wet sieve analysis is to remove all the particles which are finer than 75 micron particles from the sample so that we arrive at the correct sieve analysis results. The sample is first washed over the 75 micron sieve to remove the fine particles sticking to the sand particles. The wet sand retained on the 75 micron sieve is dried in an oven, and after drying, the dry sieve analysis is carried out in the usual manner. The finer fraction is utilized for the hydrometer or the pipette analysis, which we will learn at some point in our chemical engineering life before we graduate. Now, all I have discussed was the basics of sieve analysis. This will be further discussed basing from the laboratory experiment in a while. Now, this time, we will go to the sieving applications and its significance. So what actually is sieving in our daily life?
Before we proceed, let's try to discuss the applications and significance of sieving. Sieving, as simple as it may look, has offered a ton of applications and uses in the industrial world. Let's start from its home application so that you'll be able to visualize its practical use. As depicted on the image, flour is sieved, and this is common for bakers because this helps promote consistency in the recipe results by removing the larger particles that could potentially result in densely textured baked goods or even the ones that would sink in the middle. On the upper left corner, you can see grain cleaned after harvest. This is important as it removes unwanted materials from the grain. Clean grain has a higher value than grain that is contaminated with smaller materials like straws, chaff, weed seeds, soil particles, and stones, rubbish, and other non-grain materials, and all of these can be removed by sieving the grain through a smaller sized screen, perhaps a 1.4 mm or less sieve opening. Sometimes cleaners are included in a thresher. More applications of sieving is found on the construction sites. Sieves are used at construction sites to separate pebbles and stones from sand. In other words, separating fine gravel from coarse gravel. Sieving is very important because it is the preliminary process before construction takes place. If we skip this part, the output would be ineffective and would alter the quality of concrete, which can be uneconomical in the long run. In a chemical engineer's perspective, the same concept is used in one common industry that we may venture in the future. Screening is the first unit operation used at wastewater treatment plants, as shown in the image at the lower left corner. Screening removes objects such as rags, paper, plastics, and metals to prevent damage and clogging of downstream equipment, piping, and appurtenances. Some modern wastewater treatment plants use both coarse screens and fine screens. Furthermore, more applications of sieving can be found in food and medicinal industry. The need for sieve technology is to safeguard industrial sanitation and to clear product hygiene. Every day, millions of consumers choose products that have been through a sieve. Chocolate must be quality inspected at every transition point to prevent contamination. Cereal manufacturers want to remove oversized and undersized pieces for a more consistent product, while high quality citrus juice requires separating the pulp, seeds, and peel membrane. On the other hand, pharmaceutical manufacturing industries use sieve filter systems to prevent contamination, ensuring their products are safe for public consumption. In this industry, there are two primary types of sieving: safety screening and grading. These predetermines the process of application. In safety screening, it facilitates the correct quality of pharmaceutical products by removing contaminants like pieces of packaging and personal protective equipment. Grading, on the other hand, sorts different sized powdered particles in preparation for further processing into tablets. So that's it for the applications and significance of sieving in the industry.
Now, to further understand how sieving is done in a laboratory experiment, let's watch this
Do
video.
you have your Rotap sieve shaker, test sieves, and sample all ready to go, but you're unsure of how to perform an accurate dry sieve analysis? In this video, I'll walk you through the steps needed to ensure you get the accurate test results you're after. Let's get started. Hi, I'm Candace from WS Tyler, and I'll be your particle size analysis guide. Using a Rotap sieve shaker and a stack of test sieves is one of the most reliable ways to ensure accurate particle size analysis. Today we'll be taking a step-by-step approach on what to do in order to yield accurate and repeatable results. At the end of this video, I'll be providing an extra tip that will help ensure that you get the most out of your test sieve results, so stick around. Place your sieve stack without the sample material in your sieve shaker. Pour your sample into the top sieve. Try and pour your sample as evenly around the surface of the top sieve as possible. Once your sample has been poured in its entirety, place the test sieve lid on the top. Place the Rotap cover with the cork plug on top of your sieve stack. Drop the hammer into place. Now, set your timer and turn your machine on. Once the sieve shaker has finished its cycle, it will turn itself off. As promised, here's your extra tip. To ensure that you continue to yield accurate sieve results over time, we recommend having two sets of test sieves. One set will be your master set, while the second is your everyday working test sieve set. Master sieves shouldn't be used every day. Instead, think of them as an insurance policy. We recommend using them once a month to make sure that your working test sieves are still in spec.
Quality control is of utmost importance in construction. During a project, you never want to discover that the aggregate product you're using is ineffective or worse, unsafe. A sieve analysis or gradation test determines the distribution of aggregate particles by size. This information can then be used to determine if the material will comply with design and production requirements. A dry representative sample of material is weighed and then is placed in the top of a group of nested sieves or screen trays, arranged in descending order from the largest openings at the top to the smallest at the bottom. The stack is agitated manually or using a sieve shaker for a designated period of time, and the operator weighs the material retained on each sieve using one of two methods: the cumulative method and the fractional method. For the cumulative method, each sieve fraction, beginning with the coarsest, is placed in a previously tiered pan and weighed. As each retained fraction is added, Divide the cumulative mass by the total mass of the sample and then multiply by 100 to calculate the percent retained. Subtract the cumulative percent retained on a given sieve from 100 to calculate the percent passing. For the fractional method, the operator weighs the content of each sieve fraction separately, waiting to discard material until the test is complete. As the operator weighs the content of each sieve fraction, the operator will divide the mass retained on each sieve by the total mass and then multiply by 100 to calculate the percent retained. To calculate the percent passing, the operator subtracts the percent retained on the sieve nested beneath. Depending on the specifications for the materials being tested, the findings should include the following: total percentage of materials passing each sieve, or total percentage of materials retained on each sieve, or percentage of materials retained between consecutive sieves. Follow these tips for accurate and repeatable particle determinations. Avoid overloading sieves. Total material retained on a sieve at completion should be less than 1 to 2 layers deep. Allow enough time on a sieve shaker or testing screen for complete separations. Watch for degradation. Some brittle or friable materials can break apart during separation process, leading to inaccurate results. And regularly check the mesh for wear, tears, or distorted openings, since this can bias test results. Gilson's testing screens are designed for coarse materials of mid-range density, such as limestone or gravel, and Gilson's sieve shakers offer many tabletop options for coarse materials up to 2 inches.
So now let's move on to the next slide, which is the objectives, materials, and equipment. So basically, there are two objectives in this experiment. First is to perform the differential and cumulative analysis of a given sample, and second is to determine the particle population and average size of a sample by the case of a screen analysis. For the materials and equipment, as you can see, there are quite a few. First is the standard dialer testing sieves, that is with cover and pan, and this will be used in order to determine the particle sizes in a product and guarantee a certain quality level. Second is a sieve shaker, which is used for separation and size determination of particles by passing them through a series of chambers with mesh filters and agitating the sample in order to obtain complete separation. Beakers is used for holding or containing measuring liquids, solutions, chemical reactions, and etc. Analytical balance in order to accurately measure the mass of the sample. And brush is for cleaning. And lastly is the calcium carbonate as the dry sample of this experiment.
So now let's proceed to the procedure of the screening lab experiment. To start with, prepare a 200 grams of dry sample of calcium carbonate. Then make sure that the sieves are clean. Then if it is, assemble the sieves in decreasing order of sieve number. That is having the smallest sieve number at the topmost part of the setup. Then place the weak calcium carbonate into the top sieve and cover. Then place the sieve stack in the mechanical sieve shaker and shake at the preferred time interval. So let's say at least for 2 minutes. Then remove the stack carefully from the shaker. Next is weigh and record the retained mass of the sample in each sieve. So if there is a retained mass at the topmost sieve, then proceed to approximate the size of the retained sample on that sieve and estimate the largest diameter that could possibly be measured and record it as the diameter of the assumed preceding sieve on top of it. Then calculate the mass fractions. Also, several trials are done for the same time interval. So, are all the designated time interval for this experiment done? If no, repeat the procedure from the start for another time interval. Then if yes, that's all for the procedure of the screening or sieve analysis.
So good morning, I'm discussed about the data, equations, calculation section for. So starting with this slide, which shows the data that was recorded by previous students that did the sieving process in the laboratory. And this data will be the basis for our calculations. The next slide will be shown the calculations done using this data. So in calculating the data gathered, first must calculate percent retained each mesh as shown in the slide. Using the same process, calculate the percent retained during 4 minutes 6 minutes in the data given. Next, solve for the mass fraction, calculate average percent retained at that minute. Lastly, solve the cumulative undersize, precise, and the average particle size each mesh at the given minute. Solving for the average particle size, just solve of the screen size calculate the previous screen size. All of the data being calculated shown at the end of the presentation. This slide shows the particle population and the cumulative analysis graph. The particle population graph shows that during the experiment, the average particle size being collected are measured 0.1 to 0.2 millimeters. The undersized cumulative analysis graph shows the percent of the sample is coarser than the mesh size as it passes through during the sieve process. And the oversized cumulative analysis is the opposite of the undersized cumulative analysis. And this is the last part, the calculation section. Next, the conclusion section.
Alright, we are almost done with our topic. Now let's test our attention on how well we have understood and remember the report that has just been discussed. Let's try to sum up a couple of important things that we have learned today, most especially the definition, application, and types. They say that the best parameter of understanding is by knowing well how to explain the topic. Let's test the theory by sharing to our classmates our takeaways for today's report, and when sharing, let's try to recall what we have learned today. I'd be needing at least 2 volunteers, and while we listen to each other's inputs, let's try to pause this video for a while, please. Thank you so much for those who have shared. It's really great to know that you have understood today's topic, and for sure, everyone else who listened got almost the same thoughts and understanding, so let's proceed. I know this might be a bit redundant, but for conclusion's sake, allow me to restate the definition. So, screening or sieving is grading by size of particles of powdered or granulated material done with a sieve. Easily put, sieving is a separation technique based on the difference in particle size. The size is the one responsible for retaining the larger particles. So, the material is subjected to horizontal or vertical motion during sieving according to the method chosen. This causes a relative movement between the particles and the sieve. Then the individual particles either pass through the sieve mesh or are retained on the sieve surface depending on their size. Sieves are a critical part of the production process. Recalling a product due to quality defects or safety issues can damage the reputation and bottom line of any manufacturer. To put it back together, the key points about sieves are first, these are critical in today's pharmaceutical, food, and beverage industries, not to mention what I have said before, that it is also used for construction and for wastewater treatment for chemical engineering discipline. Then all food production uses forms of filter, sieve, or industrial food strainer. Lastly, pharmaceuticals depend on various types of sieves for product purity and hygiene. So basically, there are 2 types of sieves. Sieving that predetermines its application. So first is that it can be used for safety screening. So it facilitates the correct quality of powders by removing contaminants like pieces of packaging or other foreign materials. Second is that it can also be used for grading, which sorts different sized powder particles in preparation for further processing into assorted sized products. Let's also tackle the advantages and disadvantages of sieving. We believe that all things in this world have their own pros and cons, and let's all check what sieving has to offer. So let's go over first with its advantages. Since it's a traditional method, it does not require much skill. Also, It's a simple contraption for separation, making it a lot less cheaper than any other separation processes. Now, it also gives accurate and reproducible results that measure a wide range of sizes. Then, on the other hand, let's try to go over with its disadvantages. Now, sieving cannot separate particles with the same size. Of course, this is very clear, and one good example is when a mixture of starch and flour is sieved, it cannot be separated. Well, it just passes through the mesh hole, so it's pointless. So, of course, we also have the second disadvantage. It is impossible to use sieving for cohesive and emulsions as well as agglomerated materials such as clay. When the particles coagulate, it might clog the mesh or make it a lot more difficult to separate materials. Then third is that the minimum limit of measurement is about 50 micrometer. So beyond that would be, a lot more smaller than that would be a lot difficult to sieve or screen. Lastly, so particle attrition causes further size of reduction. What this means is that when um, materials are subjected to vigorous motion, vertical or horizontal motion, this could cause breakage on the material itself, making it a lot more smaller and could affect the quality when it passes through the mesh itself. So this can be a huge disadvantage because this could affect the quality of the products of any companies. So that's it. So let's proceed to the next slide.